Welcome. We want to take a look at an application example of exponential modeling. So we have a culture that starts with 8,000 bacteria, and after 1 hour, the count is 10,000. If we want to find a relative growth rate model, we're looking for a model that looks like A of t is equal to some initial amount times e to the RT. We know that the culture starts with 8,000 bacteria, so we know that P is 8,000. However, the other unknown here are we don't know. So we can use the initial condition or the additional condition of after 1 hour, the count is 10,000 to determine the value for R. So we have A of t in general. We can start off by plugging in our value for P. We have this form. We just have to find R. We know that A of 1 is that 8,000 times e to the R times 1, and that's going to be 10,000. I can divide both sides by 8,000 to get e to the R is equal to 10,000 divided by 8,000. Of course, it would be a good idea to simplify that as 5/4. We can rewrite this in logarithmic form. The natural log of 5/4 is equal to R, and that finds a value of R for us. This gives us a model. A of t is equal to 8,000 times e to the natural log of 5/4 times t. So that is the model that we were looking for. If you wanted to find an approximation for the natural log of 5/4, you're welcome to do so. Just read directions carefully, so that way you know if you should give exact answers or not. If it's not specified, your work should clearly demonstrate that you found an R value of natural log of 5/4, and that you then evaluated that to be some decimal approximation that you find. If I want to find the number of bacteria after 2 hours, I can do so simply by evaluating our function. A of 2 is equal to 8,000 times e to the natural log of 5/4 times 2. Now I could perform some simplification here, or in the case that you rounded this and gave a decimal approximation, that's fine. We can just punch it into our calculator right as it is. Either way you go, you should find that this is 12,500 when you evaluate. So we say the number of bacteria after 2 hours is 12,500. All right, after how many hours will the bacteria double? All right, the bacteria will double. Let's see here. Okay, the bacteria will double after how long? Let's see here. So we take our A of t equal to 8,000 times e to the natural log of 5/4 times t, and we're looking for how long does it take to double? What's the population after it doubles? 16,000. Easy enough. So I just need to solve this equation for t. Not a big deal. I can divide both sides by 8,000 to find e to the natural log of 5/4 times t is equal to 2. I can rewrite this in logarithmic form. My base is e, so I have the natural log of 2 is equal to the exponent of natural log of 5/4 times t. So I just have to divide by the natural log of 5/4 to find the value of t. I could find an approximation for that, and our approximation would be approximately 3.1062, and it continues on. So the population doubles. After approximately 3.1 hours. Excellent. So we briefly mentioned before the idea of a doubling time model. So we want to find a doubling time model for the number of bacteria in this case. A doubling time model is going to look something like this. A of t is equal to the initial amount times 2 to the t over, we'll call it lowercase a, where a is the doubling time. This should make sense for us because when t is equal to a, we would have a over a, and the population doubles, right? 2 to the first is just 2. Population doubles. All right. So we don't have this precisely at this time. If we wanted to find that doubling time model, well, actually, we do have this precisely, right? We just found the doubling time, natural log of 2 over natural log of 5/4. So we can write it as a of t is equal to 8,000 times 2 to the t divided by, we gave it as natural log of 2 divided by natural log of 5/4. Let me just double check, make sure that I copied that correctly. Natural log 2 divided by natural log 5/4. So this is our doubling time model, and that would be fine. Again, if you wanted to use that approximation of 3.1, that would be okay. You would find that there's a little bit of a discrepancy when you go to compare the two models, but they would be very close. If we wanted to find it a little bit more exact, what we can do is we can graph these to help us observe, at least visually, that these are the same thing. So this right here is our relative growth rate model. Here it is. We observe an initial population of 8,000, and after a little over 3 hours, we get that doubling time, bringing us to 16,000. So that's our relative growth rate model. I can get rid of that and then look at our doubling time model. Initial population of 8,000, a little over 3 hours. A little over 3 hours brings us to that population of 16,000 doubling time. That looks pretty good. They look about the same. If I were to plot this function back on there, you'll notice a slight color change, but they look to lie on top of one another. So I can get rid of that, add it back, get rid of this, put it back, right? We see that they appear to lie on top of one another. So if you wanted to verify this, you could take the difference, one minus the other. And if you were to do that, if they're the same, it should give us 0. So we go ahead and click on that, and you'll notice here that h is just that horizontal 0. To verify this, I evaluated h at a couple of different places. H of 1 is 0, h of 5 is 0, h of 10 is, starts to get something that's non-zero. The problem here is that we're using approximations, or at least that's what this program is doing. So here, where it's relatively close to 0, it gets good approximations, right? 1 is close to 0, so it's 0. 5 is close to 0, so it's 0. 10 is starting to apparently get a little bit further away. And if we wanted to, we could actually take a look at something like h of let's say 100, and we're actually going to find that this is quite a bit non-zero, and it's not because our functions aren't the same, it's because the approximation that the program is using is not exact, and that error begins to compound. So if I let that go, it becomes fairly significant. It doesn't seem super big, but actually at h of let's say 200, I think I did earlier, that's actually a negative. Wow, that's a huge number, right? There's thousands, millions, billions. No, I'm sorry, hundreds, thousands, millions, right? Negative 268 million. That's huge. That's enormous. So these approximations really start to go haywire as you move further. But anyway, That's just a conversation on technology and the faults that technology can have. What precedes this from here to here is a really good demonstration that yes, these two things are the same. And if we wanted to manipulate them algebraically, we certainly could do that to find that it is exactly zero. So thank you. Thank you for your time.